Let's look at the effect of temperature, that is in calculation of the internal forces in the statically indeterminate structures. The effect of temperature is just the same as it is in the statically indeterminate structures, just that there are some few adjustments here. And below are the steps that used to approach problems involving temperature changes. One of them, as we said earlier on, we first need to extract the basic shape, that is if the structure is statically indeterminate. Then after that we need to draw the bending moment diagram due to the action of the unit force, that is in bid of trying to make the structure statically determinate. And the axial force diagram also needs to be drawn, because when you're calculating for a change in temperature, we require the action of the axial force. So the two diagrams are required: the BMD due to the unit force, and then the axial force diagram due to the action of that same unit force. Then afterwards we come and find the T0 and delta T. The T0 is the temperature at the midpoint of cross section of the beam or the column. Then delta T is the temperature difference. Then after we found that, we come and calculate for delta T1, that is the change that, or the change of the effect in temperature. And after doing that, we come and solve for x1 from the equation sigma 11 x1 plus delta 1 t is equal to 0. So if you notice, we have got a difference here. Here we have a t, while the other side we had a p. So when you're dealing with temperature, we look at the change due to temperature. So we abbreviate it with the t, while for the other side we use the p, implying a force. Then after doing that, we come and compute the moment of the structure from m is equal to m1 x1 plus mp. Then after doing that, now we come and draw the final bending moment diagram by superposing the forces and moments. So let's assume that we've been given such a structure and they require us to find the internal forces, as in like that means they need us to find the moment of the structure and then the axial forces if there are any. So it's the same question they can be asked that by telling you to either draw the bending moment diagram of the system or the axial force diagram of the system. They all have the same process of calculation. So here we notice that we have a temperature of 15 degrees inside and then a temperature of negative 35 degrees on the outside of the structure. So the first thing that we need to first check on is the structure that we are having statically determinate or indeterminate. So when we look at this shape here, we see that it is one single rigid structure, and then one single rigid structure requires only 3 supports to make it statically determinate. But when we observe here, we've got 1 support, 2, so say 1 reaction, 2 reactions, 3, and then 4. So means that it has got an extra of 1 reaction. So that means we are dealing with a problem that is under the statically indeterminate structures. So we first of all need to come up with a basic structure. Our choice of a basic structure is as follows. We do add a hinge in the middle part here. Then after adding a hinge, that means that we release the moment, isn't it? So therefore, we are going to be having our basic force or our unit force as a moment which is x1, like that. So then we've got the action of temperature as a negative 35 degrees. Then inside we've got 15 degrees Celsius. So from that, we now first of all have to come and draw the M1 drawing, that is the bending moment diagram to the action of the unit force, or in this case the action of the unit moment. Since we have a force of a moment x1 pushing upwards, that means it causes the donor part here to be under tension. So the magnitude is 1, therefore the moment under this side would be equal to 1. Then likewise the moment and pulling this side causes this donor section to be under tension. So the bending moment diagram is drawn on the lower side. All of them have a magnitude 1. Yeah, even this side I can mark it as 1. So at this point we've got a rigid joint at this point here. Therefore, even here up we are supposed to be having a force of magnitude. We are supposed to be having a force of magnitude 1. So therefore, we mark it like that. Then here we have a 1. And then since we have a hinge down here, we know that at a hinge the moment is equal to a 0. Therefore, we just come and connect it up downwards to the 0 point like that. Then likewise here at the hinge we have a 0. Then at the rigid corner we have a force of magnitude, a moment of magnitude 1, like. Then for the sake of the axial force diagram, and to come up with the values of it, we shall have to split up the structure into 2. That is, let's say through this point here. Then you take only one side, like for example the right hand side or the left hand side. After which you find the moments at, let's say, such a point. Here we would be having our moment, our x1. Yeah, even this side there is that x1. So you take up one side with the moment x1, then you come and find the value of the force. If you do that, you'll discover that we shall end up coming up with a moment of magnitude that is approximately 1/6. That means that our Fn diagram would be having a force of 1/6 at this point. Even here we shall be having 1/6. So having drawn up these two, the next part is the next thing we need to do is to come and calculate for T0 and then the delta T. So from what we talked of last time, we say that our T0 would be equal to a half, like the average of the two temperatures. So it would be, which we're having 15 minus 35, isn't it? Then divide by 2. This one here would be giving us a negative 25 degrees Celsius. Then our delta T would be equal to, that is 15 minus negative 35 degrees Celsius. That gives us a temperature of 50 degrees Celsius positive. So after doing that, now we move on and calculate for the delta 1T. Our delta 1T is given by the equation summation of alpha delta T over H, then integral of m1 ds plus summation of alpha T0 integral of f1 ds. So this one here would be giving us a value that is equivalent to, we shall be having alpha into 50 for our delta T. Then our H had been given as, let's assume that we've been given H as 0.6 meters, that is 600 millimeters. Then times our M1. Yeah, so from the M1, we shall be having the moment from the rectangle. We have an area of what? Of 1, of width 1 times the length, that is 8. Then plus the area of the triangles, they are similar, so we should take a half times the base of 1, which is 6, then times its height, which is 1, then times the 2 because there are 2 of them. I hope you remember I said that for temperature, this integral just simply means the area of the shape. Then minus, it will be alpha into our T0, that is 20 times 25 times 25, then times now the area of the Fn. This is Fn1. Fn1, the area is 1/6, then times 8. So when we work out this one here, we find it that we shall be having for this side we have it as 1166 alpha, then minus 33.4 alpha. Therefore, we come up with a total value of 1133 alpha. That is as our delta 1T. Having found our delta 1t. Next we come and find our delta 1, 1. So this one here we say that's equal to integral of m1 times m1 ds over ei. So our m1 drawing has been put there. So if you remember, we say that this one you multiply m1 against itself, where meaning that we take the a from the same diagram and then the y, a is the area and then the y is the height at the center. So here it will be equal to 1 over ei, since it's a constant we can pull it out, then into, so we begin with a rectangle. So for the rectangle it's got a width of, this rectangle here, if you have to begin with it, it has got a width of what? Of 1, then it has got a length of 8, then times. Now multiplying it against itself, it will be having a height at the center, that is because as like y would be this distance here, because take it as the distance from the structure itself up to the distance from the baseline of the structure up to the point where we've got the outer boundary of the bending moment diagram. So it would be this distance from here up to somewhere here, that is a 1 also. Then here how we add on that one of the triangle. So the triangles are similar, I'll just use 1. So the area is given by a half times the base of which would be equal to a 1 times the height, which is equal to a 6, then times this height here, that is from this point up to this point. Using similar triangles, you find that this height would be equal to 2 over 3, like that. So when you come and manipulate out this, we shall find that our delta 1, 1 is equal to 12 over e over ei. Then from that, the next bit of it, we've got to come and solve the equation sigma 1, 1 x1 then plus delta 1t is equal to a 0. Then from that, we know that our sigma 1, 1 is equal to 12 over ei times x1. Then when the delta 1t crosses to the other side of the equal sign, we would be having it to a value of negative 1133 alpha. So from that, the final value of our x1 would be equal to negative 94.2 alpha ei. So having found our x1, we can now move on and draw the final bending moment diagram. So as was in the case of the action of the force, what we do is that we are going to be multiplying the x1 times the moment that is on the m1 diagram. So as we come up with m1 x1, like that. So here, when I multiply this to the rectangle, like and the triangle, all of them have got a magnitude of 1 and positive. So it's simply the value will be changing into a negative. This becomes negative 94.2 alpha ei. The same for all the other sides. So even up, let me just indicate a negative 94.2 alpha ei. So what this implies that the negative implies that our bending moment diagram should be drawn onto the opposite side of the structure. Thus the final diagram would look like this, something like that. Yeah, then since we have rigid support, even this part would be going upwards. Then I come to the left hand side and then a rigid joint, so it goes up like that. Then now here, since I have no any other force on this beam, it would just continue like that smoothly. So this is 94.2 alpha ei. So this becomes my final M drawing. So for the sake of the axial force, the diagram becomes Fn1 times Fx1 times Fn1 times x1. So meaning that I'll be multiplying all these values by negative 94.4. So when I multiply, like from the inside it will be going outward to get to that point that's equal to that. So the value here is we get 15.7 alpha ei, like that. And that is our final Fn diagram. So that's how we handle the issues of temperature statically in determinant structures. Thanks.